A closed cylindrical can is to be made so that its volume is 52 centimeter cube. Find its dimension if the surface area is to be minimum. So, we got a cylindrical can so that volume is 52 centimeter cube and height is h and radius is r. We know the formula for volume. Volume equal to pi r square times h. Volume equal to pi r square times h is given to be 52. And then we want to minimize the surface area. We will apply second derivative to minimize the surface area or second derivative test. What does second derivative test says? If a function, first point, if a function is double differentiable, so we want a function to be double differentiable. Whatever we want to minimize, we want to write it as a function that is double differentiable. Second, we want f dash of a equal to 0 for some real number a, for some real number a. So, a will be the stationary point. Third, we want f double dash a to be positive. Then we say that a is a point of minima, and in most of the cases a will turn out to be the point of minimum. Let us do it. We got volume equal to pi r square h equal to 52, and how about the surface area? Surface area equal to area of the bottom circle and the top circle. Area bottom circle is pi r square, and then top circle is also pi r square, that is 2 pi r square, plus lateral surface area, that is 2 pi r times h. Let us call this to be equation 1. We want to get surface area S as a function of r or h. S comma surface area equal to 2 pi r square plus 2 pi r h. It is better to eliminate h by 1, by equation 1. We got 52 equal to pi r square h. So, h equal to 52 by pi r square. H equal to 52 by pi r square. So, we can write equation 2h. We can write equation 2h. S equal to 2 pi r square plus 2 pi r, remember we want to eliminate h, and h equal to 52 by pi r square. H equal to 52 by pi r square. We can cancel pi out. Let us cancel pi out, and we can cancel r as well. So, S equal to 2 pi r square plus 104 by r, that is a function of S. We want a function to be double differentiable. If you want to apply double derivative, we want a function to be double differentiable. Let us define Sx. Sx equal to 2 pi x square plus 104 by x. Let Sx equal to this, comma x greater than 0. If x is positive, this is a polynomial expression, this is a quotient of polynomial divided by polynomial. Polynomial are continuous differentiable, and quotient of polynomial divided by polynomial is again continuous as well as differentiable. provided denominator is not equal to 0. So if we assume x to be positive, then this quantity is differentiable, it's double differentiable as well. So yes, f is a double differentiable function. We got it. We want a stationary point. We want f dash a equal to 0 for some real number a. Can we do so? Yes. So first case, we defined Sx equal to 2 pi x square plus 104 by x, that is a double differentiable function. So first criteria satisfied, f is a double differentiable function. Now we want to find a stationary point a, that is f dash a must be equal to 0. Once again, we want to determine stationary point, that is we want to solve for f dash x equal to 0, in this case Sx. S dash x equal to d dx of Sx, that's equal to d dx of 2 pi x square plus 104 times x to the power minus 1. 2 pi, that's just a constant. Derivative of x square is 2 times x to the power 2 minus 1, which is x to the power 1, plus 104. Derivative of x to the power minus 1 is minus 1, x to the power minus 1 minus 1, that's x to the power minus 2. Once again, we want to solve for f dash x equal to 0. In this case, we want to solve for s dash x equal to 0. S dash x equal to 0 if 4 pi x equal to 104 by x square. We simplify it out to say x cube equal to 104 by 4 pi. We cancel by 2 and say that 26 by pi equal to x cube, or x equal to cube root of 26 by pi. So did we determine the stationary point a? The answer is yes. Once again, s dash x equal to 0 if x equal to cube root of 26 by pi, x equal to cube root of 26 by pi. So s dash a equal to 0 for a equal to cube root of 26 by pi. Now third criterion, f double dash a has to be positive. So third criterion, we solve for f double dash a or s double dash a. Let's determine the sign of s double dash a. Once again, s dash x equal to 4 pi x minus 104 times x to the power minus 2. So s double dash x equal to d dx of s dash of x. Let's differentiate it out. Derivative of 4 pi, that's just a constant, we don't have to worry it about. Derivative of x with respect to x is just 1. Minus 104, that's a constant. Derivative of x to the power minus 2 is minus 2x to the power minus 3. For x equal to a equal to cube root of 26 by pi, comma s double dash x equal to s double dash a equal to 4 pi plus 108 1 by cube root of 26 by pi whole thing cube, definitely which is positive. If double derivative is positive, then we know that x equal to a is a point of minimum. So the surface area is minimum. It's a local minima, but in this case it's also a global minimum when radius equal to x equal to cube root of 26 by pi. Now we are asked what is the dimension if the surface area is minimum. So if radius is known, from this formula we can find the height of the cylinder. H equal to, now H equal to height of cylinder equal to 52 divided by pi r square. We simply using the fact that volume equal to pi r square h. 52, that's just a constant. Pi, that's also a constant. Radius equal to cube root of 26 by pi, or 26 by pi to the power 1/3, and we need to square it. Okay, now 52 by pi can be written as 2 times 26 by pi, and 1 by 26 by pi to the power 2/3. You see, by law of indices we can simply subtract these powers, and this is equal to 2 times 26 by pi to the power 1 minus 2/3, that's 1/3. So height must be equal to 2 times 26 by pi to the power 1/3, and radius equal to 26 by pi to the power 1/3. That is, we need h equal to 2 times r, and r equal to 26 by pi to the power 1/3. If we got this, then we are minimizing the surface area.